So yes, today I have a story for you about non-backtracking spectral clustering of non-uniform hypergraphs. So I want to start by saying just a little bit about what it is to cluster a hypergraph, and then we'll do some non-backtracking spectral things. So we're going to be considering, there we are. So we're going to be considering the hard hypergraph clustering problem. So in the hard hypergraph clustering problem, we observe some hypergraph data. So this is an example on the top right here. In this data, I have a collection of nodes that are joined together by edges of various sizes. So some of the edges in this hypergraph are 2 edges, others are 3 edges, and 3 edges are marked by ellipses here. And what we want to do is look at this data and assign each node to some hopefully meaningful cluster. I've intentionally drawn this hypergraph on the top right in such a way that it's not so hard to eyeball this problem. I can see, okay, if I look at the nodes, if I sort of partition them by left and right, there's only 1 2 edge that runs between those clusters. So a reasonable partitioning that looks like it could potentially mean something is to take these nodes and to just assign the left and right sets of 4, each into their own clusters. So this is what we want to do. Oh yeah.
Can I just was the segment in the first part is stand for?
Oh, sorry again.
So the line segments, what do they stand for?
So this is an abstract data structure. Any kind of pairwise relation or interaction, I'm being a little bit vague about that right now.
So are we given the hyper axis?
Yeah.
Okay.
Yeah, so we're given a hypergraph, including the nodes and all the edges, and the edges are of various sizes. So in this case, 2 edges and 3 edges, and that's what we get as data, and we want to do the cluster assignment. Okay, that help?
Yeah.
So for today, what I want to do is talk about spectral algorithms for doing this, as well as some conjectures, not proven yet, conjectures on theoretical limits for when it's even possible to do this task. And if you're interested in learning more about the details of this, the paper was actually just published last month in the Science Math Data Science. So you can go find all the details there. So what we're going to do in order to pursue this problem, this is not the only way to pursue this problem, but it's one way. We're going to take a generative approach, and we're going to treat this as approximate statistical inference in a stochastic block model. So a stochastic block model is a mythical origin story of where the data come from. And we're going to try to learn something about this mythical origin story from the data in a backwards approach. So in our mythical origin story about the data, all the nodes start with a true label that we collect into a vector Z of labels. This true label is not observed. Again, not observed. We are not assuming knowledge of this true label. We're just assuming that there is one, and our goal is to find it. Then, from this true vector of labels, we're going to assume that edges form in this hypergraph according to some rate omega of the labels in each node tuple. So if I look at a tuple R of some number of nodes, and I ask, hey, is there a hyperedge on this tuple of nodes or not? What I'm going to do is I'm going to compute this function omega on the labels of that tuple, and that's going to give me a rate of hyperedge formation on that tuple. So for example, in a picture like this one, where I've sorted the labels in such a way that hyperedges are likely to live within sets of the same label, we might have a rate function omega that has a property like this one here at the bottom, where the rate is higher when all nodes have the same label and lower if the nodes have 2 or more distinct labels. So this is a rate function of an assortative hypergraph. Lots of ways to encode this, lots of ways to parameterize the rate function. We're not actually going to deal with the specific parameterization here, and we're going to abstract that away a little bit. So problem, I want to define algorithms that will take this mythic origin story and try to recover the true set of labels Z or something correlated with it from actual data or synthetic data. before we go into real data, and it's going to be a little while before we get to real data, actually, I want to introduce a synthetic test bed for this problem. So here's a synthetic test bed. This is a place in which we're going to test a few algorithms. So what I've done is I've considered a whole set of hypergraphs here with 2 edges and 3 edges and 2 equal size clusters. And our parameters in our test bed are going to be the proportions of 2 edges and 3 edges that live within clusters versus between clusters. So for example, if most 2 edges live within clusters and most 3 edges live within clusters, we get a picture like the one here on the top right. So this is the picture we started with. Most edges stay within a single cluster. On the other hand, I can tweak things a little bit. If I say, well, most 2 edges live within clusters, but most 3 edges live between clusters. Now I'm down here, where instead 3 edges tend to cross clusters, and I can look at all other various combinations. So what I get here is this 2-dimensional space of hypergraphs with different kinds of structure of 2 edges and 3 edges that live within or between their respective clusters. And so I'm going to parameterize this with P2, the percentage of 2 edges that live within clusters, and the P3, the percentage of 3 edges that live within clusters. And if you want a very boring algebra exercise, you can express this using that rate function omega from earlier, but I would say don't bother. So this testbed is one that some co-authors and I introduced in a paper from a few years ago. So this is a paper by myself, Nate Dalt, and Austin Benson, in which we offered a modularity expression for the hypergraph clustering problem. So modularity is a fast and very dirty way to hypergraph clustering. So we introduced a fast and very dirty way to try this problem. And we tested this algorithm on this synthetic testbed. This is a pretty simple, well, in one way, simple combinatorial optimization problem over the set of possible label vectors. And we offered a Louvain algorithm, which is a very greedy and highly suboptimal way to do this, with an objective function optimized. Not going to worry about the details, that's a different talk. But here's the thing. We tried this clustering objective on this synthetic testbed, and what we got was a very bizarre result. So here in this picture, each of these pixels is a combination of P2 and P3. We sampled 200 hypergraphs with those settings of P2 and P3. We ran this modularity-based algorithm, and we measured the adjusted random index, which is one of several reasonable ways to measure how well you do at recovering the ground truth clusters. So adjusted random index of 1, yellow regions, that's where you perfectly recover the planted clusters. Adjusted random index 0, that's the black regions, random noise, purple and orange in the middle. So what we observe is that this modularity algorithm succeeds in some regions of this testbed. For example, on the far right, large P2, most 2 edges are within clusters. It also succeeds when P2 is small, but P3 is large. So that's kind of interesting. But there's also a lot about this plot that I think is frankly extremely strange. So for example, if you squint a little bit, you'll notice that the algorithm occasionally succeeds down here, but not at all consistently. There are these very bizarre gaps in the plot as well. I think the most bizarre is the one on top there, where the algorithm just totally suddenly fails to detect anything correlated with the right answer in this specific weird little gappy area, but also what's going on here, what's going on here. I think it's a frankly bizarre plot, and the more I give this talk and reflect on the fact that we published this figure, I think it's even stranger and stranger. So the question that motivated the topic that I have to talk to you about today is, hey, can we do better in this synthetic testbed? What actually is the best we can do in this synthetic testbed? Can we actually find clusters that are correct or correlated with the correct answer in some of these weird regions, can we learn something about what's possible and not possible?
So there's a small strip at the top of this diagram.
Yeah.
Can we interpret it a little bit, and especially around the 1, 1?
Oh yeah, up top there. So that's a result of the certain parts of the graph actually becoming disconnected. So it's a bit of a degenerate case.
Okay. So,
Yeah.
am I right that the more combinatorically available 2 edges than 3 edges? Or is it the way around? Is it that way around? It's not the same number, are there?
No, there aren't. So one thing, a detail that I've kind of not bothered to tell you about here is that in order to specify a hypergraph, you also need to say the mean degree of each node in terms of 2 edges and 3 edges. In this particular visualization, the mean degree is 5 for each one. So each node is connected to on average 5 2 edges and 5 3 edges. So if you count numbers of edges, they're the same numbers of each kind of edge per node. But if you count things like how many nodes am I connected to through 2 edges, how many nodes am I connected through 3 edges, then you start getting different answers. Okay, so the team for this project is myself, Professor Nicole Eichmeyer in the Department of Computer Science at Grinnell College in Iowa, USA, and Dr. Jamie Haddock in the Department of Mathematics at Harvey Mudd in California, USA. And the paper that just came out, Non-Backtracking Spectral Clustering of Non-Uniform Hypergraphs. So the remainder of this talk is the story of that paper and how we filled in some of the gaps in this weird diagram. So what we know about generative clustering in graphs, and I'm going to be a little bit intentionally light on detail here, considering our time restrictions. So I'm very happy to talk to folks more about this if that's of interest. What we know about graphs from a series of lovely papers from the 2010s is that if you have a random graph, so a graph stochastic blockmodel with 2 equally sized groups, with each node having on average A neighbors of its own label and B neighbors of its opposite label, as illustrated up top, then, theorem, it's possible to find clusters from data correlated with the correct labels, the ground truth, if and only if this expression relating A and B is sufficiently large as the number of nodes goes to infinity. So in a large range of graphs, you need this signal to noise ratio, is in fact how you can think of it. You need the signal to noise ratio to be sufficiently large in order for it to be possible to do the detection problem. And what I mean here, what's impossible is a really low bar right here, actually, because I'm not talking about finding the right answer. I'm not talking about finding something that is 50% correlated with the right answer. I'm talking about finding something that is correlated at all with the correct answer. If this ratio is insufficiently large in this random graph, you cannot even find something that is correlated with the truth. So what happens in synthetic experiments is you look at measures of the gap here, and you'll try whatever algorithm you choose. I'm going to emphasize this is not a property of a specific algorithm. This is an information theoretic threshold. You'll try some algorithm, and for a while you'll be doing just no better than random guessing at all. And then suddenly you hit that threshold, and then you start seeing better than random performance. There's this really sharp phase transition in what's possible here. So this is the big picture of what we know about graphs. So there's another wrinkle, which is that there are matrix methods based on eigenvectors and matrices that are asymptotically optimal for the detection problem. And what I mean by asymptotically optimal is that whenever this signal to noise ratio is large enough, whenever this task is possible for any algorithm, these matrix methods will succeed in this task. So they're optimal in the sense that whenever this task is possible, they can do it. They are one of the things that can do it. Okay, so we want to do this clustering problem. We want to do it whenever it's possible in hypergraphs. We don't know when it's possible yet. We got to figure that out. But what we know about graphs is that this is a place where there are optimal matrix methods. So what we want to do for hypergraphs, the strategy here is to find matrix methods for hypergraphs that have some candidacy of being optimal and then form conjectures based on that. Problem. Matrix methods for hypergraphs sounds good, but what's your matrix? You got hypergraph, there's a lot of different kinds of matrices you can choose. As I think probably 1,000 papers in the last 5 years have now asserted, projecting hypergraphs, projecting hyperedges into cliques loses information, ignores higher order interactions, and all these introductions of papers claim that's a bad thing. So we'll see if that's how true that is in a bit. Another thing we could do is to construct a series of adjacency tensors. So just a straightforward generalization of the adjacency matrix, one adjacency tensor for each possible size of edge. This is a very adequate data representation, but problem we want to do eigenvector stuff, and eigenvector stuff is non-trivial for even a single tensor, and I don't know that anyone has any good definitions for what it means to consider eigenvectors as sets of tensors of different dimensions. Seems like something that's not that likely to be well defined to me. So we're going to try doing something else. And I don't claim to have exhausted all the possibilities here, but there's just highlighting that there are a few candidates that are difficult in different ways. Our candidate here is the non-backtracking operator. So the non-backtracking operator, obviously it's non-backtracking, which is why it's traditionally labeled B, but we'll do with that what we can. So the non-backtracking operator, also often called the Hashimoto operator after its introducer. So the non-backtracking operator, it's a matrix that operates not on nodes, but on edge node pairs. The parsing just kind of the symbols here, I think, is a little more trouble than it's worth. The idea is to consider a nice walk on hypergraph. And what I mean by a nice walk is that I'm going to start on an edge. So I'm going to start on edge E1. I'm going to pick a single node in E1 that I'll call V1. And then I'm going to pick a new edge, but I'm containing V1. But I'm not allowed to pick the edge E1 that I was just on. I have to pick a new edge. Okay, so I pick E2, different edge, also contains E1. Now I have to pick a new vertex in E2, and I'm not allowed to pick the previous vertex, V1. I have to pick a new vertex in E2. And so I keep going on here. I pick a new edge and then a new vertex that isn't the vertex I was just on. I pick a new edge that isn't the edge I was just on, and so on. So when you visualize a walk from nodes to edges to nodes in hypergraphs, you're probably visualizing something like this. The non-backtracking conditions here eliminate the funny backtracking pathological cases that you're probably not visualizing. So this is a well-behaved walk on a hypergraph.
So can I interpret as, well, the vertex B here always corresponds to an overlap between two hyperedges?
Yeah, so the vertex V here, and when we talk about walking here, we're always going to go from one edge containing a node to a new edge containing that node. Sorry, did that address your question?
Yeah.
Okay.
So in other words, we are actually constructing a graph that's that characterizes how hyperedges overlap with each other.
You can construct that graph, yeah. This is a nice construction here that you can actually find. I'm not going to use this construction so much in this talk, but you can actually find this construction in my little source here. So this non-backtracking operator was developed for graphs by Hashimoto and then introduced for hypergraphs by Christopher Storm in this paper, the zeta function of a hypergraph. And Storm actually makes good use of this construction where we can think of this as a graph of directed edges that are joined to other directed edges in runway. That's a very valid way to think about it. In that case, this matrix B would be the directed adjacency operator for that graph. Yeah, absolutely. So an interesting wrinkle about the non-backtracking operator for hypergraphs is that it was proposed 17 years ago, and then I'm going to say rediscovered without citation by a group in 2015. So that's a little fun note. Do your research, everyone. First theorem about this. In a random graph, so by which I mean a stochastic block model, like the testbed that I showed you earlier, with two equal-sized clusters within cluster k degree a sub k. So that means a node has, on average, a sub k edges that connect it to other nodes of the same label, and b sub k edges that connect it to nodes with different labels. In this stochastic block model, the non-backtracking operator B has an in-expectation eigenrelation. So we didn't do the full concentration of measure random graph theory here. We just calculated an in-expectation eigenrelation. If someone wants to do the random graph theory, then please, I guess. Anyway, the non-backtracking operator has an expectation and eigenpair with eigenvalue beta and eigenvector V, where beta has a value that we're able to calculate in terms of these parameters, and where V, the eigenvector, is correlated with the true planted clusters. So I've illustrated this theorem on the right here. On the top, I have the spectrum of the non-backtracking operator for a synthetic hypergraph that I've generated. You can find the eigenvalue closest to its predicted value. Then you can get the corresponding eigenvector. And that corresponding eigenvector, it's a node edge vector, so you need to add it up over all the edges in order to get something on the level of nodes. And once you do, if you look at the signs of that eigenvector, so label 1 nodes on the left, label 2 nodes on the right, the signs of the entries of this eigenvector correlate with the true labels. So if I were to use these signs here as a labeling algorithm, I would be right much more often than random. So this is already a candidate matrix that has some properties that we know will help us for clustering. One issue. Computation. This non-backtracking operator B is indexed by edge node pairs. And the problem here is that hypergraphs have a lot of edge node pairs. In particular, the size of this matrix is m times the m is the number of edges times the average edge size. And our problem here is that this is too big. A small data set like the contact high school data set that everyone in the States loves. This data set has about 300 nodes, about 8,000 edges, and average edge size about 2.5. So 300 nodes doesn't sound so bad, but the size of the non-backtracking operator is 20,000 by 20,000. And yes, it's sparse, but that's still a bit uncomfortable. So I want to do eigencomputations, but that's a little bit big. Fortunately, there's a little bit of quick linear algebra that can help us out. Theorem, under relatively mild conditions, if lambda is an eigenvalue of the non-backtracking matrix, so we want to know about eigenvalues of this matrix. If lambda is an eigenvalue of that matrix, then either option 1, it is boring. Option 1, it has one of these limited sets of values, and its eigenvector carries no structural information. Or lambda option 2, lambda is also an eigenvalue of the different and often but not always smaller matrix B prime here. B prime, it looks a little bit hairy. It's just composed of various components that convey different kinds of structural information. about the hypergraph. So I here is the identity matrix. Bold A is the adjacency operator for each hyperedge size arranged in a set of blocks. D is the degree operator, again arranged in a set of blocks. K is a diagonal matrix of possible edge sizes, and so on. So there's a lot of structural components here that we need to combine, including some parameter products, in order to get this new matrix that we can compute on. This matrix is of size 2k bar n, where n is the number of nodes and k bar is the number of distinct edge sizes. And if I am lucky, this can be a smaller matrix for it. The proof is actually really nice. It doesn't require much more than the following determinant identity, called the push-through identity sometimes. So you essentially write out your non-backtracking operator as this nice little expression in terms of simpler operators that also have some good relations. Then you follow as a push-through identity, and you actually come out to find that the determinant of lambda I minus b, the determinant that you care about for eigencomputations, factors in terms of this component, as well as a bunch of stuff that you don't care about. So it's an equivalently elementary proof in some ways, although the algebra gets a little bit shaky. So back to our computation issue, if you compute on B prime this reduced matrix instead of B, you can actually work with a matrix with a little under 2,000 by 2,000 entries instead of 20,000 by 20,000 entries, and so that can be a significant speed up. Not always. This matrix is not guaranteed to be smaller, but it often, in fact, usually is. Okay, so this gives us the components of a first kind of proper algorithm. What I'm going to do is I'm going to compute the second eigenpair, so it's provable that this eigenpair, when it exists and is findable, is the second one. So I'm going to compute the second eigenpair of this reduced matrix B prime. And if the corresponding eigenvalue is real, I need that. If it's not real, I'm kind of a little bit stuck. But if it is real, then I can take the corresponding eigenvector. I have a little bit of aggregation here to do to get something that corresponds to a signal on nodes. And once I have that signal on nodes, I'm going to consider the sign. And that sign is going to give me a predicted cluster label. So illustrated here. And I can generalize this if I want to do multi-way clustering or need more eigenvectors. Okay, so this is a first algorithm with a bit of probabilistic justification, but does it work? In terms of data and synthetic experiments, last time we were here from a previous paper with these funny gaps. So we tried this algorithm that we developed here, the spectral method, and we thought, oh, spectral methods are asymptotically optimal for graphs, and maybe we solved the problem. So we tried it out, and here's what we found. When I look at this picture, the way it makes me feel is that I would call this result more rational. It doesn't look silly in the way that the other one looks silly. My algorithm is working when most edges of size 2 and 3 are within cluster, or when most edges are between cluster, but not necessarily when they have conflicting signals. So this doesn't look weird in the same way as the other one, but there is something else weird about this. Because look, my Louvain algorithm, for all its flaws, it was succeeding here and succeeding up there. Whereas this non-backtracking algorithm is not. So I know that I have not found the asymptotically optimal approach to this problem because I have an example of a different algorithm succeeding where this one fails. So I have a reasonable start, but I have to do something else. Yeah.
You said this demonstrates you haven't found the asymptotically optimal one, but actually this doesn't prove anything but the asymptotics, right? Because if your graphs get larger and larger, maybe it does, maybe Louvain starts failing even where in the previous plot it is.
Oh yeah, no, fair enough. Mathematically, experiments don't exactly prove on finite cases. What I can say is that I will soon show you an experiment where we do better than this. How's that? Okay. So the different thing we're going to do starts with belief propagation. So belief propagation originally kind of made its way into the computer science and machine learning community from physics, as the cavity method of statistical physics. Belief propagation is an approximate method for what I used to call statistical inference, but now for branding reasons I call machine learning. Finally, belief propagation, it's a discrete time dynamical system. So these latter two perspectives are going to be perspectives that are important for us today. So for the stochastic block model that we're considering, this mythical origin story about where our data came from, what belief propagation asks us to do is to define this massive array of two different kinds of variables. So here it is focusing on the mu variables. So here a mu I, R, and S is a belief that node I has about its membership in group label S based on what it has heard from node tuple R. And if you're looking at this and saying, well, gee, there's a lot of possible node tuples in a hypergraph, this seems like too many variables, then you're right. What we know about belief propagation is that when your hypergraph is sufficiently sparse, belief propagation is going to give you an arbitrarily good approximation to the right answer. So what sufficiently sparse means is the subject of several papers that I don't want to get into. So what we know about this is that this is a statistically grounded way under reasonable assumptions in order to do the hypergraph clustering problem. However, this is, forget the update itself, this is just too many variables to like store. So we can't really do this. So I feel like I'm making a theme here. We're going to cheat. So what we're going to do is we're going to consider a certain special case that fortunately corresponds to the synthetic testbed we've been studying so far. So consider a stochastic block model in which every node has the same expected number of attached edges for each possible edge size. So this is a symmetric situation. Nodes in group 1 and group 2 both have the same expected number of edges of size 2, size 3, etc. And furthermore, none of the expected degrees depend on the number of nodes n. So a little more formally, we're considering a sequence of increasingly large hypergraphs, and we're saying that the degrees in expectation are going to remain constant. Then, theorem, the belief propagation algorithm has an approximate fixed point that I'll call x bar. And this fixed point contains no cluster information. What's going on at this fixed point is the fixed point where belief propagation says, hey, every node is equally likely to belong to either cluster. So no information in that. But taking a dynamical systems perspective, what we're going to do is we're going to consider what happens if we perturb belief propagation a little bit away from that fixed point. Now, what we'd like to understand is whether belief propagation is going to then move away from that fixed point in a direction that is informative for us about the cluster structure. And what happens when you perturb a discrete time dynamical system around its fixed point is governed by the Jacobian of the dynamics. So fortunately, you compute the Jacobian of the dynamics for this belief propagation algorithm around this uninformative fixed point. And it turns out that all the entries in the Jacobian are very, very small, vanishing as n grows large, except for a specific block. And this specific block is a sum of outer products between CK, the matrix of parameters. This matrix of parameters depends on the parameters for our stochastic block model. And BK is the Hashimoto operator, or non-backtracking operator, restricted only to edges of size k. So I take my hypergraph, I look only at the edges of size k, I compute the non-backtracking operator for just that part of the hypergraph, and I form a sequence of matrices this way. So I actually get this nice expression for the Jacobian in terms of this matrix of parameters that I need to be able to compute somehow. And BK, the non-backtracking operator, restricted to edges of a fixed size. So, from a dynamical systems perspective, what I can now do is I can analyze the spectral structure of this matrix J, and if this matrix tells me that the uninformative fixed point is unstable, I can say, what are the unstable directions? And I can hope that those unstable directions will lead me toward cluster structure, because those are my estimates of where the algorithm will go if it's perturbed from the uninformative fixed point. So, that said, one more cheat. I said that B was a kind of an inconveniently large matrix, and now I'm computing Kronecker products, so that's not a good look. So more cheating. This is approximately the same theorem as before, it just involves more inconvenient algebra. Instead of computing eigenpairs of this matrix J, I can compute eigenpairs of a usually smaller matrix J prime. This matrix J prime is of size 2 times the number of nodes times the number of possible labels times the number of edge sizes. So it is still big, but it is usually less big than the alternatives. This leads us to a new algorithm, Belief-Propagation Hypergraph spectral cluster. So what we know is that we can approximate belief propagation locally around this uninformative fixed point by considering the spectrum of this matrix J formed of parameter matrices and non-backtracking operators, or alternatively, this usually smaller matrix J. This gives us an alternating algorithm that we can work with. So we're going to start by guessing the parameter matrices C sub k. Then we'll form this matrix J. And what we're going to do is we're going to compute the real eigenpairs of J with eigenvalue larger than 1 in magnitude. So larger than 1 in magnitude comes from needing to find the unstable directions of this uninformative fixed point. The restriction to real eigenpairs is because I'm still talking about perturbations in the space of probability distributions. So I need those to remain valid probability distributions under perturbation. So I can use the real eigenpairs with eigenvalues larger than 1 in magnitude. I'm going to sum these over edges, and the result is going to give me a Euclidean embedding of the nodes based on this eigeninformation. I'll then cluster in the Euclidean space using your favorite Euclidean clustering algorithm. Then, based on that set of candidate clusterings, I can re-estimate my parameters in my parameter matrix, and I can repeat the convergence. This algorithm has a bit of the flavor of an EM algorithm. So I try to figure out which clusters the nodes are in based on my guessed clusters. I'm going to update some parameters. I'm going to repeat this over and over again. It has an EM algorithm flavor. Weirdly, this is not an EM algorithm because there's no objective function. There's no likelihood. So we're not actually optimizing anything. So it has a bit of that alternating flavor, but it's not really mathematically related. Yeah.
And do you know how many eigenvectors are used in Spectral?
Yeah, so no, unfortunately. This is something that's interestingly hard about this problem. In graphs and uniform hypergraphs, it's possible to say how many there should be if you know how many clusters you're looking for. Unfortunately, here, there's no such guarantees. You can sort of construct counterexamples where it's just wildly impossible to say what the right number of eigenvectors is to compute before you've done any analysis. So this is why we just say, hey, get all of them with eigenvalue larger than 1 in magnitude where the eigenvalue is real. This is not computationally convenient. I'm not claiming this is computationally convenient. I'm claiming we're going to learn something about the theoretical limitations. So yeah, definitely opportunities for more computationally convenient approaches here.
So what does the matrix C sub k converge to?
Those are going to converge to your estimates of rates of interconnection between the two clusters. So remember I had these parameters A sub k and B sub k. So A sub k, then expected number of edges within that connect a node to other nodes in its same cluster. B sub k, the expected number of edges connecting it to other nodes in the opposite cluster. Here's the thing. In order to estimate those parameters, I need to know which nodes are in the clusters. If I don't know which nodes are in which clusters, I don't know how to estimate those parameters. So P sub k is built out of those parameters. I haven't given you the formulas because the formulas are boring, but it's collecting those parameters.
So if there are more than 2 clusters, then all the matrix here will be a tensor, right?
If there's more than 2 clusters here, in this particular case, the way C sub k is going to look is that it's just going to have 1 row and 1 column for each cluster. So 2 clusters, 2 by 2 matrix, 3 clusters, 3 by 3 matrix.
Okay, so the product here is protected.
Yep. Yeah. Yeah. All matrices. I never took a class on tensors, so all matrices. So a bit of a visualization for what this algorithm does. So what I've done is I've formed another synthetic hypergraph, and I've computed the spectrum of the Belief-Propagation Jacobian over here on the far left. And I picked out all the eigenvalues of this Jacobian that are real and larger than 1 in magnitude. I highlighted them in red. There are 8 of them, but we don't really know a way to predict that. We just found that there are 8 of them. Then what you do with these eigenvalues is you take their corresponding eigenvectors and you aggregate them up so that they have 1 index for each node and 1 index for each possible candidate cluster. And this hypergraph I generated with 3 clusters, and I'm going to assume that we knew that for now. So I aggregate these eigenvectors up, and what I get are a bunch of columns that I can think of as feature columns for my clustering problem. Some of these columns are totally uninformative. For example, the columns that I got from the first 2 eigenvectors here are not useful at all. They kind of say the same thing for every node, not really much information. On the other hand, as I sort of look at some of these later columns of features, I can see, oh, the signs of these eigenvectors that I've aggregated up do actually correlate with the partition that I planted in some way. If I collect enough of these and cluster them, then I might be able to recover something approximating the planted clusters in this data set. Just to illustrate here on the far right, I haven't actually done the clustering problem. Instead, I just embedded these 24-dimensional points in 2-dimensional space to convince you of the fact that points in the same cluster are nearby in this feature space. That's all that picture is trying to say. Okay, so I have a new algorithm. How does it do? So last time we were doing a plain spectral algorithm with a non-backtracking operator. We got this picture, which we know is not optimal. But when we incorporate this additional structure of belief-propagation, we have more involved computation to do. There's more steps. There's eigenvalues need to be computed from larger matrices. But we do get an interestingly different picture. So this time, we're actually able to succeed everywhere that this funny Lubin algorithm succeeded from at the beginning, and also everywhere that the original vanilla non-backtracking clustering was able to succeed as well. Notice that when I say succeed, I'm not always talking about getting higher ARI. I'm just talking about getting non-zero ARI. Whenever those other algorithms did. A few things to notice. First of all, the region of failure where we don't detect anything correlated with ground truth is suspiciously round. And secondly, there's also this fun little, I'm going to call it an orbit around that region as well. A fun fact is that we can actually describe both of these analytically. So the orbit is from an eigenvalue collision problem where the relevant eigenvalues you care about actually cross. They induce noise in their corresponding eigenvectors and it muddies the classification a little bit. And then this region of undetectability here, or conjectured undetectability, can be described kind of nicely. It's an ellipsoid. And we can actually tell you exactly its shape. And when I say tell you, I'm talking about a conjecture, not a theorem. So conjecture in this synthetic test bed that I described to you, spectral clustering, using this Belief-Propagation Jacobian that we described earlier, fails to detect clusters inside this ellipsoid with these parameters for the centroid and the radii. Here's the experiments. So we believe that our algorithm fails inside this region. A nice point is that we can actually consider the first version of this algorithm as a degenerate special case. So we can actually write out the boundaries for that algorithm as well. Again, this is a conjecture. The proof requires a lot more random matrix theory than any of us know how to do. So if anyone here is really good on random matrix theory, then please have at it. We would love to see your proof. Additionally, reasoning by analogy to what we know about graphs, we believe and conjecture this is not just a fact about spectral clustering, it's actually a fact about any algorithm. We believe that this task is actually information theoretically impossible within this region. But again, that is a conjecture, and we would love for someone who knows how to prove this to go ahead and prove this for our problem.
So we don't even take care of the running time of the errors of error, right?
Nope. Nope. So there actually are interestingly different regimes here. So in graphs, there's one regime where the problem is impossible. There's another regime in which the problem is possible but cannot be done in polynomial time. And there's a third regime where the problem is even. So I'm not talking about the running time here at all. So I think it's about time for me to wrap up. So what I'll say is that if anyone wants to talk to me later about a quick little data example where we made a map of mathematics using this algorithm and found that we got moderately better results than a graph algorithm using this one. Here's a little map of math based on some stack change using this model. We don't claim that this is really the best model that people should use in practice because it's limited to some of its assumptions and it can be pretty slow. We do claim that we think this model can help us understand some of the theoretical limits of the clustering problem. So if you want to talk about examples, we'll talk about examples. So with that in mind, I'll finish up. What I've argued for you today is that belief-propagation spectral clustering can help us form conjectures about when the possibility of clustering a hypergraph exists, when that task is possible. Not easy, not up for interpretation, not hard, but possible. Proving these conjectures, however, is likely to require some powerful machinery from random matrix theory and discrete probability that maybe someone in this room is up for. We have not gotten there yet, and I would guess we're probably not going to get there, but you never know, I guess. And finally, there are some nice linear algebra tricks with the structure of the non-backtracking operator that allow us to make things a little bit faster. I'm not claiming that they make things practically faster in a way where you would want this to be your go-to algorithm for data analysis, but it does help. So with that in mind, I would like to thank my awesome collaborators, Nicole Eichmeyer at Grinnell College and Jamie Haddock at Harvard Med College. Our paper is recently out in the Science Journal Math on Data Science. And if there's a little time, oh, there's not time. Okay, so no time for questions, but I'm happy to ask. Oh, we can? Okay, that's allowed. Okay.
Let's take the speaker first.
Oh. Everyone.
But it wasn't clear in the algorithm, do you have to choose P1 and P2 before you apply it, or do you infer those parameters?
Oh, yeah. So,
can you repeat the question?
Oh, yeah. So the question was, do we have to choose P1 and P2 before we try this algorithm, or are we going to infer it along the way? And the answer is that we're going to make an educated guess. So, in particular, I've glossed over these details a little bit because the algebra I feel is very boring. P1 and P2 are one way of describing A and B, the rates of the number of edges, or sorry, the mean degree within cluster and between cluster. And this is alternatively described and handled in this matrix DK. So what's going to happen is that as we run this algorithm, we are going to iteratively update estimates of parameters that are equivalent to P1 and P2 and generalize them.
Are there any situations where you can imagine you're in the top left or the bottom right? Those contradictory.
The top left and the bottom right. This is, I think, the fundamental practical question. Of essentially the value proposition of hypergraph clustering, actually. So I didn't show this in this talk, but there are some experiments that are in this paper and also in the modularity paper, where what we find is that when you're in the bottom left or the top right, hypergraph clustering works well, but also actually just graph clustering works well. Those regions are easy for both. So if you want to argue that hypergraph algorithms beat graph algorithms, you don't make that argument here or here. You make that argument here and here, because you can imagine in this region, projecting down to cliques is going to give you kind of contradicting information. You can even tune the parameters where the projection will look basically like an error transfer graph. So that means for these kinds of models, these hypergraph clustering algorithms beat graph algorithms when edges of different sizes carry different kinds of cluster information. The dark confession is that it's surprisingly difficult to find data where that appears to be what's going on. We have found a few cases where these models do very well. So for example, this like famous high school contact network is one where we seem to do very well. And from the inferred parameters by the models, you can actually say, okay, the hypergraph models believe that edges of different sizes do carry slightly different information, not this dramatic, but slightly different information that a graph projection wouldn't pick up on. So I do think that this is a kind of phenomenon that does exist and can be taken advantage of, but I think something that people who work on hypergraphs don't want me to say to you is that it's rarer than anyone would like you to think. I got a job now, so I can say that.
Just a quick question on like maybe the last slide. We showed lots of these pictures. Yeah, this one. What's different in these four images you write? What are the differences between these?
Oh yeah, great question. So why are these all different? So the way these are all different is that I do things like mess with the mean degrees. For example, this picture is the one I showed you 1,000 times. This picture has, instead of 2 edges and 3 edges, it has 3 and 4 edges of various degrees. This picture has 2 and 4 edges of different mean degrees. And I'll emphasize, I can consider arbitrary numbers of different edge sizes. I'm just choosing 2 at a time here for visualization purposes.
Okay. Go ahead. Well, so how can we describe the direction of the episode? Because I mean, we can't just describe it with only its centroid and its radii. So for example, for the first
oh yeah, it's axis aligned.
It's always aligned.
Yeah, it's an axis aligned ellipsoid. Sorry, I should have said that.
But for the first one, can just treat it as degenerate
Yeah.
ellipsoid.